So in this final video, we're covering lesson number 3 in part 2 of Unit 5 for college algebra. I have just 2 more problems that I'd like to chat about, and these are kind of interesting examples here. And following this discussion, next week we'll get into our review for the Unit 5 exam. So I'd like to perform the same analysis that's been done on the other rational equations. We should find the vertical, horizontal, and oblique asymptotes. We should identify any holes or other interesting behaviors of this graph so that we can sketch a graph and understand the behavior of the function without the use of a graphing calculator. So I'm just going to jump down here and rewrite this problem. So this is question number 1, and the function f of x is equal to x to the 4th minus 16 divided by x squared minus 2x. Now, as I would on any of these examples from this week, I would factor first, and I recognize that x squared minus 4 times x squared plus 4 would represent the numerator, and in the denominator we've got a common factor of x, so I'll call this x minus 2. Now, what makes this one kind of interesting is that we've got an additional difference of squares here that can be factored further, and I'll call that x plus 2 times x minus 2, x squared plus 4, and then again x times x minus 2. And so these factors, x minus 2, will factor out and therefore produce a hole in the graph. And so I'll address that in just a moment, but first off, let's talk about the horizontal asymptotes. Now, since the degree of the numerator is larger than the degree of the denominator, there are no horizontal asymptotes. But also, we'll note that there are no slant asymptotes either, because recall that on a slanted asymptote, the numerator's degree has to be bigger than the denominator's degree by exactly 1, and we don't have that here. The numerator's degree is bigger than the denominator's degree by 2, and as a side note, x to the 4th power divided by x squared equals x squared, and this x squared graph does describe the end behavior of this rational function. This end behavior of the rational function is going to tend to look like a parabola. And we'll come to that in just a moment, especially when we check our work on Desmos. So we have no horizontal asymptotes, no slanted asymptotes. What about vertical asymptotes? As far as the vertical asymptotes go, we want to look at our simplified or factored example. So after the x minus 2's are factored out, we're left with x plus 2 times x squared plus 4 over x. So the only value that makes this fraction undefined is when x itself is equal to 0, so therefore our vertical asymptote occurs when x is equal to 0. Now, if I'm thinking about the sketch of this graph, when there's a vertical asymptote at x equals 0, then that tells me that there are no y-intercepts. There are no points where the graph is going to touch or cross the the y-axis. So there are no y-intercepts. But we might want to make note of this here. The y-intercepts we know occur when x is equal to 0, but when x is equal to 0, if I were to substitute that here in the factored form, or even back here in the original form, which would probably be more appropriate, when f is evaluated at 0, we end up with an undefined result. So when f is evaluated at 0, we get an undefined result, so therefore there are no no y-intercepts. As far as x-intercepts go, that occurs when y is equal to 0, when our function is equal to 0. And for this one, I do like looking at the factored form. So when does the numerator equal 0? Well, for this one, I like to look at the factored form before any of our factors canceled, although it may not make a big difference, but just out of habit, I always look at this one right here. So we know that 0 would equal x plus 2 times x minus 2, times x squared plus 4. So when any of these factors equals 0, then the entire expression will equal 0. So that tells me that at x equals -2, at x equals +2, and then, well, this one doesn't produce any real number result because this would occur when x is equal to the square root of -4, which is 2i, an imaginary number solution. So at first glance, it looks like I have two real number x-intercepts and two imaginary number x-intercepts. But as we described a little bit earlier, the number 2 is going to produce an undefined result. So when x is equal to 2, we're actually going to produce a hole in the graph, not an x-intercept. So that gets canceled. I won't be able to plot it. This one gets canceled. I won't be able to plot it. The only x-intercepts that I have are at -2, or is at -2, 0. So no y-intercepts, one x-intercept. We have a vertical asymptote at x equals 0. So we're not working with a whole lot right now. Here's our vertical asymptote. We have an x-intercept at -2. So let's see if we can identify where that hole exists. I know that the original function is undefined when x is equal to 2, but if I were to substitute the number 2 into this factored component back here, then we should be able to establish a coordinate that might fit, or that should fit on the graph, but will exist as a hole. So here again, anywhere that there was an x in this factored form, I'm going to substitute the number 2 in its place, and this will help me locate the hole. This ends up being 4 times 8 divided by 2. So 2 and 2 made 4. 2 squared was 4 plus 4 made 8. And we're dividing that result by 2. So it looks like 16 to me. So evidently there's a hole at the coordinate 2, 16. And so in order for that to fit on this particular sketch, I'm going to have to adjust my y-axis scale just a little bit. And so to do that, I'll mark each grid line with a value of 4. So when x is 2 and y is 16, I'll have a hole in the graph. And those are the only two data points that I've got to go with in order to sketch the rest of this graph. And so I don't really know what to do from here. I don't have enough information as far as our analysis goes, so I'm running out of ideas. The option at this point would be to use test points. And here's where a calculator comes into play, albeit one without the use of a graphing tool. If I select some test points, then I can evaluate what the x and y coordinates are that exist elsewhere on this graph. So what I think I'll do is I'll just use some test points that exist over here. Well, I don't know, let's say -5, -3, -1, +1, 3, and 5. If I use those 6 data points, that should give me a pretty accurate representation of the behavior of this function. I don't need to go much further beyond that because that should, again, give me the shape surrounding this vertical asymptote and surrounding this hole. And then the end behavior is going to tend towards some sort of parabola in nature. And we'll hopefully see that when I draw this graph on Desmos. So again, we're just using test points here because our other analysis really didn't give us much more information to go with. So let's use an XY table and our TI Inspire, only in calculator mode, to go ahead and test these points. Now the first thing that I'm going to do, much like I did with the polynomials unit, is I'm going to create this function using the letter a instead of x. So we have a to the 4th power minus 16 divided by a to the 2nd power, or a squared, minus 2a. Now the calculator doesn't understand what to do with that, and so it actually tried simplifying the best that it could. But we're not interested in the simplified result. What we would like to do is evaluate our function at specific a values. So I'm going to set negative 5 to a, and I'm going to store that in place of letter a. This way, when I go back up to the original expression and press enter, the a value will be executed as a number, negative 5, and then the result would be simplified. Now, I would like to note that there is an error message here, and it's stating that the domain of the result, this output, might be larger than the domain of the input. So when we see an error message like that, kind of like we had a hole or excluded values in our graph, I want to be sure to execute the original function at the supplied a value or x value and not the simplified form, because this one could give you an answer for a value of a that doesn't exist in this original form. Now, graphing 87/5 is hard to do, so I just pressed Control Enter and I got the decimal equivalent, which was 17.4. Now, I'm going to do the same for an x value or a value, in this case of negative 3, and so on. So negative 3 stored as a, and then I'll press the up arrow until this is highlighted, tap enter, and then enter again. If I press Control Enter, that'll turn my fraction into a decimal, and I've got about 4.3, and so on. And if I plot these data points on the scale that I just established a second ago, let's see here, at negative 5, we got a y value of about 17, so that's right about here, I would guess. We have x value of negative 3 and a y value of 4, that's right about here. X value of negative 1, y value of negative 5. X value of 1, we jump way up to 15, that's way up here. And x value of 3, we've got a y value of 21, that's approaching value that's out of reach, and then an x value of 5, we're at 40. We're way off the scale here. So, well, what's going on? It's still a little bit hard to tell, but it almost looks like on this left side we've got this tail that's forming almost like a snake curve. We can bound this right side by the vertical asymptote, and the left side kind of, it's tending towards an upward trajectory. But on the right side, we don't really have that. I almost might think that it does the same, where it races upwards in this direction, and then it might turn down here towards the vertical asymptote. But I actually know that that can't happen because there are no additional x-intercepts. And so I might make a note of that right down here. You know, these have to stay positive because there are no other x-intercepts, and then the graph, because of that, has to turn upward. And so we haven't seen anything like this before, but this curve here might give us an idea. It's kind of reaching a low point and then turns upward towards this vertical asymptote. It can't turn downward, again, because that would have produced some sort of x-intercept down here, really, really close to 0, but it could have turned upward and not approached the x-axis anymore at all. And now, if I reference back to this parabola idea, just that we established a little bit before, do you kind of see the parabola that's being formed here now? If I look at this outer edge and deviate from this weirdness in the middle, if I connect this left side tail and this rightermost right side tail, it almost looks like this is starting to look like a parabola. In fact, if I were to do the long division with x to the 4th power minus 16, and I'm going to give myself some space here, x to the 4th power plus 0x cubed plus 0x squared plus 0x minus 16. If I were to do the long division of that with, what was the original here, x squared minus 2x, in a similar fashion as the last video, I should be able to obtain some sort of quadratic here that would represent the behavior of this function. So let's check that out. So I always start by asking myself, x squared times what will equal x to the fourth power? And as it turns out, x squared times x squared will equal x to the fourth power. So there's my initial guess. I'm going to put an x squared here. And I am keeping that in line with the other x squareds. And as I multiply my initial guess by x squared minus 2x, I get x to the fourth minus 2x cubed. When I subtract these two, this leading term cancels, and 0 take away a negative 2x cubed is 2x cubed. And I can bring down these remaining terms. And I'll now ask myself, x squared times what equals 2x cubed? X squared times what equals 2x cubed? And to me that looks like 2x. So my next guess is going to be 2x. Now 2x has to be multiplied by this divisor, and that produces 2x cubed minus 4x. And in the long division algorithm, we'll subtract these. Leading term does cancel out again, which is nice. 0 minus negative 4x squared is 4x squared. And I think this is going to be my last step, even after I bring down these remaining terms, because really what I'm interested in is the expression, the polynomial expression here. I'm not really interested in the remainder at this point. So one more time, I'm going to ask myself, x squared times what will equal 4x squared? And I can jot that down over here. X squared times what equals 4x squared? And of course that number has to be 4. X squared plus 2x plus 4. And so what I think is going to happen is the left side tail and the right side tail, sort of talking about this end behavior here, I think the left side and the right side tail are going to follow this parabola. Y equals x squared plus 2x plus 4. And that'll give us an additional component to check our work against when we go out to Desmos. Without the use of a graphing calculator, I would expect you to be able to establish this shape. The only time we really needed a calculator at all was to complete our test points. So I think that's fair, but no graphing tools should be needed prior to this. So now let's go out to Desmos and see what we can see with regards to this original function. What does this equation look like? Well, here we go. I will zoom out just a little bit, adjust the scale. Actually, before I adjust the scale, let me just zoom out. So there's that unusual shape that we were talking about, how the left side tail seems to be diving down and approaching that vertical asymptote, and the right side tail had to turn up and away. We thought that there was a hole located at 2, 16, so it does look like that there is a point there. It does fit on the graph, and so that, along with our other test points, did generate this shape. Now if I zoom out and really aggressively change the scale here, hopefully you can see the parabola that we were mentioning before. And then also, if I graph that parabola, x squared plus 2x plus 4, you can see how closely the original graph now mimics that outside end behavior. So if we zoom in really close on a, I suppose, micro level, this rational function doesn't look much like that parabola whatsoever, but on a macro scale, if we zoom way out, then we do see how similar they are. So for extremely large values and extremely small values, these two functions behave very, very close to one another. But for these values in the center, if you will, of the parabola, they don't quite behave like we would expect. Now I was just trying this on another computer, and I want to see if this works this time, because it did on my desktop computer. Let's see what happens if we zoom way in on this this hole of this graph. Yeah, there we go. So this is what I was trying to describe in the other video. If we zoomed in really, really closely on this particular graph at this location, turn off that dot that we had plotted manually, right? If I'm looking at this from any distance whatsoever, it doesn't really look like there's anything wrong with this graph. But at the coordinate 2, 16, there is a hole in the graph. And Desmos, being an online tool, if you will, it sort of breaks down. The graphing engine or tool that's being used to create these data points kind of fails at this location, as it should, because we can't really establish a point at an x value of 2 in this particular equation. And so, in a sense, their way of showing this hole is by allowing this graph to kind of break down. And if I were to try to click and drag my pointer on a data point as we get close to this position, we keep getting notified that at an x value of 2, the calculated y result is undefined. And so there's kind of a visual representation. Well, may not be the most accurate representation, but at least it's visual confirmation that there is a hole at that point in the graph. So that was fun. Let's try another one. In example number 2, I'm going to call this one g of x so that when I graph it on Desmos, it won't compete with the other function f of x. But we've got 3x squared minus 3x over 2x squared minus 5x minus 3. So I'm going to perform the same analysis as I did before. Look for the horizontal and vertical asymptotes and slanted asymptotes if they exist. We can locate our intercepts as well as any other key data points and try to sketch this graph. So the first thing that I'll note is that there is a horizontal asymptote at 3/2. I know that I can divide these two leading coefficients because n is equal to m. The numerator's degree was equal to the denominator. As far as our vertical asymptotes go, we need a factored form. And when factored, we get this, and we end up with two non-removable discontinuities. So our vertical asymptotes have to exist at x equals -1/2, and again at x equals 3. From here, I might look for x and y intercepts. The y-intercept tends to be a little bit easier to identify, because if I set x equal to 0, and I'll use a different color to make this stand out, this term goes to 0, 0, 0, and 0. Well, now I got 0 divided by 3, which is 0. So again, when x is 0, y computes to be 0. So we've got a y-intercept at that location. As far as an x-intercept goes, well, we want to find when the numerator equals 0. And I set this factored form equal to 0. That's going to occur, of course, when x is equal to 0. We knew that already. And then also when x is equal to 1. So again, one of our x-intercepts occurs at 0, 0, which happens to be the same as the y-intercept. And then we have another x-intercept when x is 1, y computes to be 0. So at this point, we've got a lot of information to work with. Let's see if we can sketch an accurate graph based on the data so far. We have a horizontal asymptote at 3/2, that's 1.5. We have vertical asymptotes at -1/2, x equals -1/2. And we also have another vertical asymptote at x equals 3. So we're going to have at least 3 segments or 3 branches to this graph. We have a y-intercept at 0, 0 and an x-intercept at 0, 0. That doesn't help too much. But we also have a y-intercept at 1, 0. That's kind of interesting. But that is really all that we have. We don't have any other data points. And while I might be able to guess what's happening in the center here, I know we're somewhat bounded by this horizontal asymptote, but we're strongly bounded by the vertical asymptotes. I kind of think that there actually might be a U shape occurring in the center here. We have no idea what's happening on the outside edges, and so here again is another example of where a test point or a series of test points might come into play. I'm going to take this U shape off just in case my guess was incorrect. And let's come up with some test points. So to get an accurate picture, I'm going to use x values of -5, -3, -1. That gives me these data points here. I don't want to use +1 again because I already knew that, so I'm going to jump up to +2, and then 4, and then 6. I think that'll give me a pretty good idea of what we're dealing with. I'm going to compute these function results off screen, and I would encourage you to do the same. You can pause the video now and resume playback in a moment to check your work. And so these are the results that I got from my calculator, and something interesting is happening right here. So maybe we'll make a bit more of an obvious statement as we look a little bit more closely at it. But again, at -5, we had a y value of 1.25. That's here, let's say. Then we have 1.2, so that's just a little bit lower than that. But then we get a y value, oops, sorry, wrong spot. At -3, we had a y value of 1.2, and then at -1, we had a y value of 1.5. Well, that's the same as the the horizontal asymptote here. So that's kind of interesting. Let's go to 2. When x is 2, we get a y value of -1.2. So that's down about here. When x is 4, we get a y value of 4. And when x is 6, we ended up with a y value of 2.3. That's right about here. So on the right-hand side, I'm pretty confident in saying that this graph is bounded and captured by the horizontal and vertical asymptote. Down here in the middle, I think the same thing has occurred from what I described just a second ago. We get this U shape that might strike these coordinates and turn downward. It's captured by the vertical asymptotes here. But this is kind of strange. There's a bit of a dip, and then the graph itself is touching the y-intercept. So I'm going to evaluate this function now at, say, -0.75. I want to see what's happening right here. And when I calculated that off screen, I got a y value of 2.1. And so that tells me that there's a data point right here. So that gives me a little bit of a clearer picture. It does look like, or I'm guessing, that this graph is going to follow this vertical asymptote, cross the horizontal asymptote, dip down, and then come back up and level off towards the horizontal asymptote towards the left. And in the first video this week, I did say that that was possible, and sure enough, I'm guessing that that's what's happening here. And if I jump over to Desmos to take a look at this, I think that's exactly what's happening. We can click and drag on the screen and see our x and y results for the coordinates along this graph. And as you can see, the y coordinates from the left side moving to the right do tend downwards for a little while, 1.2, 1.2, 1.19, and so on. And then all of a sudden they turn back upward and race upward towards infinity at this vertical asymptote. Along this center, we do have that U shape, kind of an off-centered U shape that we started to see with our test points. And then on the right-hand side, we have this more traditional leg or branch that we're used to seeing. So we could zoom out and perhaps better see the horizontal and vertical asymptotes and recognize how close to our sketch the actual graph really is. So these two problems were quite lengthy to complete, but it's this type of analysis that I think makes you a better math student. When you use your patterns and procedures that we've learned in the past to develop new understanding of more complicated examples, that's really what higher level mathematics is all about. And so I would encourage you to keep working at these types of problems and complete the extra examples that are provided in Math Excel, or you can see me for extra examples too, just to increase your skill set and make yourself better at this sort of analysis. If you've got any questions on what we covered today, by all means, please reach out to me. Send me a message through Schoology or an email, and I'll do my best to respond as quick as I can. Thanks for watching.